All right, so we'll start the final presentation on rare energy infrastructures. Take it away whenever you're ready.
Okay, yeah, so our group, our project was working on deep learning for rare energy infrastructures in satellite imagery. I'm Tyler.
And I'm Matt.
And so basically for this project, we trained an object detection model on overhead imagery in order to detect energy infrastructure. And so the issue is when doing this, the energy infrastructure are very rare, and so it makes it hard to acquire large amounts of training data, which can be used to train the model and get better results.
Yeah, so to combat this problem, we proposed creating synthetic imagery. So to do this, we used a virtual world creator called City Engine to import 3D models and then randomize their placement on pre-created landscapes. And then we took overhead imagery with a virtual camera, and then we got these colored and black and white segmented outputs that we could use for training.
Right, so the roadmap for this project was first to create and process a dataset of real satellite imagery, and we would train our model with this, and this would be our baseline. Then what we did next was created synthetic data using City Engine and imported energy infrastructure models. And then finally, we supplemented the data set of real satellite or overhead imagery with this synthetic data set that we made. And then we compared these results that we got with the baseline.
Yeah, so taking a quick look at our data, we have overhead satellite imagery from across the United States of various power plants. And for this project, we focused specifically on wind turbines as our power plant type. So to actually train our model, we couldn't just use this raw imagery. We first obviously had to label it. So we used a program to create bounding boxes over the wind turbines in our imagery by hand as the ground truths. And then we pre-processed it a bit more by splitting it into patches that could be easily fed into the model and helped improve efficiency of training.
So after this, after getting these baseline results, we then created synthetic data. This was done using City Engine and using a Python script in City Engine. We compiled a list of images and models, and then generate random scenes, randomly place these models on top of these images, and then the camera would be moved overhead in the overhead position, and it would take photos.
Yeah, so for a quick overview of what our experimental setup was, we had two different data sets, the first of which was just our regular 1,200 real images of wind turbines. We would train our model on this data set and then test it on 661 real images that the model had not been exposed to before, and then looked at its performance. And then we created our second data set, which is the same as the first data set, plus an additional 441 synthetic images. We trained our model again on this, and then tested it on the same 661 images, and then compared the performance of the model on this data set with the previous one.
And so before looking at these results, you have to understand the metrics that we're using to analyze the performance of the model. We're using precision and recall. For this project, you can interpret precision as the out of the objects that the model did classify as wind turbines, what fraction of them were actually wind turbines. And for recall, interpret this as out of the number of total wind turbines, how many did it correctly identify. And for this project, we were prioritizing recall because after running this model on overhead imagery, it's a lot easier to remove the misclassified turbines than find undetected wind turbines.
And so we can look at the results that we got. When we trained with only the real data in our training set, we got a precision of 0.813 and a recall of 0.825. And then when we added in our synthetic data to the training set, we got a decent improvement in precision to 0.831 and only a small improvement in recall to 0.827.
And so looking at the actual output, it performs very well on large wind turbines. However, in California predominantly, there are these small wind turbines, and it is inconsistent for the performance on those. And so in the future, we would like to create synthetic imagery that has high quality small models to improve the performance on these small wind turbines. We'd also like to observe the performance as the amount of synthetic data is varied, and then also apply this on a large scale to satellite imagery to locate wind turbines throughout the US, and then eventually use these same techniques on other types of energy infrastructure.
Thank you guys for listening. Here are a couple of different links related to our project. We have the project website at the top. We also have a GitHub repository of our code, the synthetic data set that we created, and then a link to the Energy Data Analytics Lab website.
Yeah, so we can send the link for the website in the chat. Matt, can you do that?
Yeah, I got that.
So we would be happy to take any questions.
Cool. Thanks a lot. So folks, please feel free to post questions and comments in the chat. I guess while people are thinking about and framing their questions, my assumption is when you say small wind turbines, what you mean is you mean not as well resolved wind turbines, and that if you had higher resolution images, you know, if I had a very high resolution image, I assume that, you know, wind turbines are largely have the same structure as you go down in scale, so that, you know, these small wind turbines here would look fairly similar to the large wind turbines if the resolution was higher. Is that accurate or is that not accurate?
That is not accurate. In California, you can see in this image on the right, there's actually there are what we call large wind turbines on the right, and those are the ones that are correctly identified. And on the left, these are small. So these are actually like different sizes in real life.
Oh no, I understand they're different sizes in real life. I'm saying what distinguishes them in terms of sizes, in terms of the images you're looking at. Is it the length scale of the wind turbines to the landscape? Is it the resolution of the wind turbines? Like the pixels per turbine?
Oh, I see. Okay. Well, yes, there are less pixels per wind turbine for these smaller ones. And there's also less shadow. Just one thing.
And so I guess the question would be, is if you could figure out whether it was the shadow or whether it was the pixels, that maybe sort of give you, I mean, maybe both of them are equally important, but my bet would be that one of those would be more important than the other. I don't know if you have a sense of that or not, or, yeah.
I would guess that would be the pixels.
No. I mean, that makes sense, yeah.
So actually to follow up on that, imagine if you had, so this imagery here is 1 meter per pixel. So if you had imagery that was 0.1 meters per pixel, how well do you think you could do compared to your performance now, roughly speaking?
Okay, yeah, that would significantly improve the performance on the small wind turbines. Yeah, there are a lot of cases, just qualitatively looking at the data, where for these small turbines, you practically can't see any of the actual turbine, and it's mostly just the shadow.
Yeah.
That's how you can identify it. So
yeah, that makes sense.
The resolution is very important.
Donald Pepke asks, what do the decimal numbers on the wind turbine images mean?
So those are confidence scores. It's a combination of how confident it is about the classification and the confidence that there's an object contained within the box. But for this, there's only one classification, which is wind turbines. So it's basically how confident it is that there is a object within the box.
And then Varun Nair asks, I think the problem is that he's getting at is the poor performance on the smaller turbines due to the poor performance generally on smaller bounding boxes or due to the poor resolution of the boxes themselves. Yeah, and I think that was what we were just kind of discussing. Varun, did you want to follow up on that comment at all, or were you happy with where the discussion went?
I was just clarifying what your question was, but I think I have two other smaller questions.
Yeah.
To your point about the synthetic imagery, did you guys generate different sizes of wind turbines and then put those into the synthetically generated imagery? Because I guess if you were to generate smaller wind turbines, that would also help with prediction of smaller wind turbines in the real imagery.
Yeah, so the experiment we showed was our basic setup. We did, after getting the synthetic data that we made for that experiment was just large wind turbines. And after performing that experiment, we then moved on to creating smaller wind turbines. But the results with those, they need to be worked on, and the improvements were not significant.
Okay, got it. And my
That's part.
Yeah, so I guess like to speak up to that point, that might have something more to do with the model itself at not being the best at detecting small images, because even in the actual training set, it wasn't doing a great job of classifying the synthetic small wind turbines that we created. So when we tested it on the real versions, it still performed poorly.
Yeah, that's a good point. I think generally speaking, it's harder to pick out the smaller boxes. The other question I had was, I was wondering if you have looked into any sort of gradient visualization technique to see what exactly the model was learning in the images. I'm curious to see if you're able to feed in one of these images through the model and see whether or not the model is focusing on things like the shadow, for example, or the actual structure of the wind turbine, since in my experience, the shadow has been really helpful for picking out these wind turbines. So I was wondering if you have been able to investigate that at all.
That would be really cool, but we have not done that, and that might be something we want to do in the future.
One question I'd love to throw out there, so let's say that the Data Plus program decided we love this work and we want to give you $100,000 to continue it, okay? Now, after your joy and celebration around that, what would be, you think, the most impactful thing that you could do if you wanted to be able to improve performance for these systems going forward? And the sky's the limit. You can create data. You can, whatever you can dream of, you can go for it here. What would be the next steps?
Definitely purchasing better wind turbine models is the first step. I assume one maybe an extra thing you could look at would be using like a GAN or style transfer to create synthetic imagery. I assume you could do that, and that would probably be a lot more realistic.
Yeah. And I don't know how much money it would really take to get this, but perhaps just higher resolution overhead imagery of the real data set would probably help with the
that's right.
results.
Yeah. Good ideas, guys.
Is there a sense of how expensive it is to get 1 meter per pixel versus 0.1 meters per pixel in terms of like cost or even reasonability, or like even if that's a reasonable proposal?
I'm not sure about that.
What are the highest resolution satellite images that you encountered through the project?
So, like just based on purely satellite imagery, this was probably the highest resolution we got, and it was 1 pixel per per 0.3 meters, was it? Or is it per
Yeah.
meter?
Yeah, and that's the highest commercial satellite, 0.3 meters per pixel. So actually, if you wanted to get 0.1 meter per pixel, you'd actually have to get an airplane and collect that imagery by flying over, which is actually very much doable. There's actually a full data set on that for the state of Connecticut from 2016, but it's exceedingly expensive in the tens of thousands of dollars range for data collections in local areas, never mind entire states.
It's actually still surprisingly cheap. I thought it would be more than tens of thousands.
Well, I mean, I'm talking about for like one, that's probably like one city.
I see.
Something in that range. If you were collecting that, if you wanted to do something that was at the state level for a large state, I mean, you're in the hundreds of thousands, if not pushing above that.
Yeah.
Yeah. It's intense.
Yeah, absolutely. And I mean, with the synthetic, one of the things that's nice about the synthetic data, though, is that you can have arbitrary resolutions, right?
Exactly.
So you can kind of see when those switching points are and everything.
Yeah, you can adjust that camera height,
Yeah.
and by doing that, simulate whatever resolution you want to. I mean, there's a nuance to that too. You have to make sure that the angle, all of the angles make sense for what would be in a real satellite image. And I know actually that was one of the things that Tyler and Matt, you guys were working on, right? Looking at or discussing with Bohau about the potential for varying kind of the angle so the sun didn't always shine from the same location.
Yeah, increasing the variety of the synthetic data is something we definitely want to do just to make the model more robust and increase the generalizability. It should and the performance. So.
And as Varun was saying, the shadows could be a really important part of identifying the turbines in general. So I'm wondering if you're training this and failing on things where there's not much of a shadow. I guess maybe that's what I'm asking is like, what's the sensitivity? You train some model. It seems like there could be sensitivity about the time of day the picture was taken, right? And the angle of the sun, and the latitude and the time of day. What is it? Longitude is up and down. That's going to affect what type of shadows you can even get out of these things. If you're at the equator at noon and you're straight up and down, maybe that's just going to kind of break whatever model you've trained.
Yeah, even the camera angle is something that is in the real data set. Some of the images will be, you can see, well, it's like a very clear different angle where you can see the majority of the pole, while others is like directly from overhead.
Right. Yeah, that makes sense.
And then you guys also explored the impact of leaving one city almost entirely out. Well, not almost entirely out of, or one state entirely out of the test data to see how things transfer geographically. Can you share a little bit about how that ended up working out?
Yeah, so what we did for an additional experiment was to exclude all of the data from California and Arizona from our training set and use them as our validation testing set. And then what we did was we created synthetic data that was meant to mimic the data that we observed in California and Arizona and look at how it performs on this novel domain and also these novel variation of wind turbines. Because in the training set for that experiment, there would be no small wind turbines. The results were not significant, and the precision did decrease. So I think main thing is getting a higher quality model for the small wind turbines. I think that would be probably the first thing we do.
And Tyler, just so I understand, you're saying that by training on synthetic data alone, that your overall predictive rates didn't really degrade that much, right?
The recall of the model increased very slightly, assuming because it would perform a tiny bit better on or slightly better on the smaller turbines, but the recall decreased.
No.
The precision decreased.
Astrid Gunley asks, how did the group choose the states to be taken out of the data set?
So that decision was mostly just qualitatively based. We noticed when we were annotating the data that a lot of the really small wind turbines were mostly all from California, and they also tended to be in the same type of geographic region, which was different from most other states. So we figured that would be the biggest challenge to, or the biggest room for improvement on just testing without those states and then including them in testing.
We wanted to pick a geography that was self-similar, but as different as possible from the rest of the data set.
Yeah.
But it seems like also that, when you just train the model on the non-California, Arizona states, what did you see happen to the performance as without the synthetic data? Just trying it, making sure the training data didn't have some of the test data locations in it. What did you see for performance on the test data set?
The performance was very bad, as you'd expect. So that just indicates that the model is not very robust or good at generalizing to these different domains, but also it hasn't seen these small wind turbines before. So I don't think that's, you can't just attribute it to not being able to generalize because it hasn't actually seen small wind turbines, and they are fairly different. And that's kind of expected. If it hasn't seen examples of a model, then it's not going to perform well on them.
Well, that's a real opportunity there, right? Being able to, major performance decreases as you cross geographies, then potentially being able to use some of the satellite imagery to overcome that. Like you said, you saw some improvements in recall there, and recall and precision. Recall is a pretty important one when it comes to finding these types of objects. So there's actually a lot of some real positives out of all of that.
Are there any other things that folks want to direct the conversations towards, ask questions about? Oh, did you ever post the, would you mind posting the project website in the chat?
Matt, did you do that?
Did it happen? I didn't see it or I missed it.
Thought I had done that, but I guess it didn't submit. Let me get that up real quick.
So I think, yeah, so I think we'll close the session there. Thank you all very much for coming and participating. And it was 4 really nice poster presentations. So thanks a lot to the students for doing a really nice job with all these projects. Yeah, give my Zoom round of applause. Yeah, and it's been great working with all of you this summer. So I guess I'll let, if anybody wants to the link rather than to take a screenshot, I'll stay for another few minutes, but I think we'll call it there. So thanks a lot, Al, and congrats on finishing the program.
Thank you.
Yeah.
Thanks.